In this screencast we're going to continue with the theme of computer-aided molecular design. We're going to stick with the group contribution methods by Joback and Reid from 1987 with their increment data, and this time we're going to go for something a little bit more complicated. We're going to try and design a branched alkane with a boiling point of 470.5 degrees C. So we have an objective function to minimise the difference between the target value and the estimated value, and if we come down here we are going to vary these groups here because these are the groups that we can use to make a branched alkane, and the CH3 groups are going to be determined based on these values. So for every CH2 there's no branching, so we don't need extra CH3s, but for this CH group here with 3 bonds to it we're going to get branching, so we'll need extra methyl groups to cap off the different ends of those branches. And for these C groups with 4 bonds, then we'll need 2 times that because we're going to get more branching, we'll need more methyl groups. So if we go to solver, that is set to minimise the objective function by varying these 3 cells, and those cells should be integers, and just to constrain the problem a little bit we've got them to be less than or equal to 20. Obviously if you couldn't find a target molecule with those constraints you might want to increase those values of 20 to even further higher values. So we're going to press solve. Solver has now found a solution. Click OK, and it's saying that we need 5 methyl groups, 5 CH2 groups, 1 CH group and 1 C with 4 bonds. So that if we use those to design a molecule we should get close to the target property. We can also do this for haloalkanes. This time we've got 2 constraints, 2 target properties. So we want a boiling point of 540.8 and a freezing point of 259.2. So this is a branched haloalkane. The objective function is to minimise the differences between those two. And this time the methyl groups, the number of methyl groups, it again depends on the number of CH and the C groups, but we're subtracting the number of alkanes, the number of halo groups present. So in solver we've got all the things set up in terms of integers, and we can press solve there just to point out that the methyl groups have to be greater or equal to 0. Press solve there. Solver is now looking for a solution by varying all these things. Okay, so solver's now found a solution. We can click OK there. The objective function has been minimized. We've got target properties very close to the estimated properties are now very close to the target values that we had, and it's saying that we need 4 methyl groups, 5 of these CH2 groups, 1 CH group and 1 carbon group there, and an iodine. So we can build a target molecule based on those and come up with a branched alkane that's going to hopefully have the target properties that we're after. So that has been a brief introduction to how we can use group contribution methods to guide us and target sort of molecules with particular physical properties that we might be after.